and welcome to another video from explainingcomputers.com. This time it's my 4th annual update on the state of play in quantum computing. This video is mainly going to focus on what the pioneers in the area have been achieving in the past 12 months. However, as usual, I thought we should start out with a brief summary of what quantum computing is all about. The microprocessors in conventional or classical computers are built from billions of transistors that are turned on or off to represent a value of either 1 or 0. In turn, this allows classical computers to store and process data using binary digits or bits. In contrast, quantum computers process information using quantum bits or qubits. These can be created in many different ways, for example using superconducting electronic circuits or by trapping ionized atoms, as I'll discuss later in the video. Unlike classical bits, qubits can exist in more than one state or superposition at exactly the same point in time. This allows a qubit to assume a value of 1 or 0 or both of these numbers simultaneously. In turn, this potentially enables a quantum computer to process a far higher number of data possibilities than a classical computer. Indeed, in theory, quantum computers will be able to accomplish tasks which are impossible to perform using conventional hardware. Today, quantum computing remains in the research phase, with all quantum hardware created for experimental purposes. This said, many traditional computing companies are now developing and operating quantum computers, with key players including IBM, Google, Alibaba, Microsoft, Intel and Honeywell. There are also a whole host of pure-play hardware and software startups, including 1QBit, CQC, D-Wave Systems, IonQ, QCware, QSimulate, Quantum Circuits, Raco, Rigetti, Xanadu and Zapata. You can find out more about what these companies are doing on the quantum computing page on explainingcomputers.com. Quantum computers will only become a viable commercial technology when they can perform useful calculations that cannot be executed on a classical computer. Back in 2012, Professor John Preskill coined the term quantum supremacy to define this concept, writing that in the era of quantum supremacy, we will be able to perform tasks with controlled quantum systems going beyond what can be achieved with ordinary digital computers. In October 2019, Google claimed to have achieved quantum supremacy. As it reported, a team of Google scientists had used a quantum processor called Sycamore to sample the output of a pseudo-random quantum circuit. Sycamore took about 200 seconds to sample one instance of a circuit 1,000,000 times. In comparison, the Google team estimated that a classical supercomputer would take about 10,000 years to perform the same calculations. As the team went on to conclude, quantum processors based on superconducting qubits can now perform computations beyond the reach of the fastest classical supercomputers available today. To our knowledge, this experiment marks the first computation that can be performed only on a quantum processor. Quantum processors have thus reached the regime of quantum supremacy. The Google announcement was big news, but soon controversial. Not least, IBM published a blog post in which they stated that the computations in Google's experiment could be undertaken on a classical computer in 2.5 days rather than 10,000 years. As IBM went on to contend, because the original meaning of the term quantum supremacy, as proposed by John Preskill in 2012, was to describe the point where quantum computers can do things that classical computers can't, this threshold has not been met. IBM and Google are rivals who have created quantum computers based on the same kind of superconducting Josephson junction qubits. It's therefore perhaps not surprising that IBM disputed Google's achievement. However, and more broadly, IBM and some other quantum computing specialists increasingly question the importance of the quantum supremacy concept. Not least, they are concerned that future experiments which demonstrate quantum supremacy may involve tasks with no useful or commercial application. Whilst the quantum supremacy debate has raged, the last 12 months have seen a notable expansion of cloud-based quantum computing, or quantum computing as a service. The birth of QCaaS dates back to May 2016, when IBM launched the IBM Q experience to make a quantum computer available over the internet. Just under 2 years later, Chinese e-commerce giant Alibaba followed suit with its superconducting quantum computing cloud. This was developed with the Chinese Academy of Sciences, and like IBM Q, allows users to run quantum programs in the cloud and download the results. In October 2018, Canadian quantum computing pioneer D-Wave Systems also made available a service called Leap to provide cloud access to its quantum computing hardware. And in January 2019, rival quantum computing pure-play Rigetti launched its Quantum Cloud Services, or QCS, platform. The big quantum cloud news of the past 12 months has been the entry of Amazon and Microsoft as new market players. Amazon's QCaaS offerings were announced on December 2, 2019, and include an AWS solution called Amazon Bracket that allows scientists, researchers and developers to begin experimenting with quantum computers from multiple hardware providers. Specifically, customers can access hardware from D-Wave Systems, IonQ and Rigetti, which means they can experiment with quantum computers based on 3 different qubit technologies. In addition to Bracket, Amazon also launched the Amazon Quantum Solutions Lab. This is intended to help companies to get ready for quantum computing by allowing them to work with leading pioneers. So, a key thing that Amazon is doing with its quantum computing offerings is to act as a broker in the cloud. On May 19, 2020, Microsoft entered the fray when it announced Azure Quantum. Whilst Microsoft is working with several universities to develop its own quantum hardware, for its current cloud offering, it's adopted the same strategy as Amazon to partner with those who already have quantum hardware and software solutions available. This allows Microsoft to offer its Azure Quantum stack, which it describes as an open cloud ecosystem offering access to a diverse set of quantum resources, including pre-built solutions, quantum development tools such as simulators and resource estimation tools, accelerated classical hardware, and a variety of quantum hardware. One of the developments that's most captured my own attention in the past 12 months has been progress in trapped ion quantum computing. Key players here include the University of Oxford, as well as a company called IonQ that in October 2019 secured $55 million of funding. The technology page of the IonQ website explains what trapped ion quantum computing is all about, and really is an excellent learning resource. In simple terms, trapped ion quantum computing creates each qubit by removing an electron from an atom in order to turn it into an ion with a positive electrical charge. A chip, known as a linear ion trap, is then used to hold chains of ion qubits in 3D space, where they can be manipulated and read using lasers. All of this is extremely difficult to achieve and control, not least because the qubits need to be supercooled to almost absolute zero, as well as being isolated in a very high-quality vacuum chamber. In addition to IonQ, another key player is Honeywell, who in June 2020 announced that it had used trapped ion technology to create the world's highest performance quantum computer. Clearly, others may take a different view. But regardless, this is another important development, particularly as Honeywell reports that JP Morgan Chase is already experimenting with its system to develop quantum financial services software, including fraud detection and AI trading applications. Always when I make a video about quantum computing, I get questions about how quantum computers are programmed. At present, this takes place using a classical computer as a control device, with the languages used including Python. An explanation of exactly what is involved is well beyond the scope of this video. But if you want to learn more and actually experiment, go to the IBM Quantum Computing website and click on For Developers. Next, select Try Qiskit, which will allow you to experiment with this open source development environment. One great but still quite complex example shows how it is possible to estimate the value of pi using a quantum phase estimation algorithm. As you can see, the Python code begins by importing relevant libraries before progressing using commands that will be pretty familiar to those with some programming background. Absolutely, this is complex and something you need to get your head around. But what I hope it makes clear is that quantum computing is not quite so removed from traditional computing as many people believe. Quantum computing is yet to become a commercial reality. This said, as we've seen in this video, significant progress continues to be made, and I remain confident that some kind of quantum hardware will find useful application in the second half of this decade. But now that's it for another video. If you've enjoyed what you've seen here, please press that like button. If you haven't subscribed, please subscribe, and I hope to talk to you again very soon.